Last time we talked about probability distributions in general. One of the things we talked about are how there's two types of probability distributions. There's continuous and discrete. Today, we're going to talk about an example of a discrete probability distribution. And then next time, we'll talk about an example of a continuous probability distribution. That'll wrap up chapter 12's content. We're not going to do any assessment other than the chapter 12 homeworks this semester. When we get back next semester, we'll do like a little review and then kind of bang through the quiz and the activity and the test for chapter 12 in second semester. Figure nobody needs anything else crammed in here at the end. Everybody cool? Hi, Jake. Yeah, go ahead. Thanks, brother. Sure. Do you need your tablet to verify the printing or anything?
I already did.
Oh, okay. I don't know how that works. All right. So today we're going to be talking about an example of a discrete distribution. That's called the binomial distribution. So a binomial distribution is a probability distribution obtained from the outcomes of a binomial experiment. For a situation to be a binomial experiment, we need to have the following properties. There's a known number of trials. We'll represent that quantity with the letter n. Each trial has only two outcomes, success or failure. The outcomes do not have to be equally likely. They can have any kind of probability attached to them they want, although the sum of the probability of success and the sum of the probability of failure has to equal 1. The probability of success is constant. That being said, all the trials are independent of one another, so the success of one trial doesn't depend on whether the previous trial was successful or not. So if we have the number of trials, and the probability of success, we can figure out everything else to find the probabilities inside of one of these binomial experiments. And as noted earlier, the probability of success and failure have to sum to give us 1. We mentioned that. So the notation that we use to denote a distribution is binomial in nature is we take our random variable and we say it follows the distribution. That's what the squiggle means. The B means binomial, where n is the number of trials and p is the probability of success. And those two quantities will describe every possible binomial distribution, just knowing the n and the p, the number of trials and the probability of success. So determine the probability of getting exactly 2 heads in 3 tosses from a biased coin where the probability of heads is 2/3. So back in last chapter, to do a problem like this, we would have drawn a tree diagram, right? So just to kind of review what we have been doing. So we have 1 toss, heads or tails, the probability attached to each of them. And we draw 2 more branchings for the second and third tosses. And then I collect what are the possible outcomes here. And I identify which ones have exactly 2 heads. So these 3 outcomes have exactly 2 heads. I'll calculate the probability of each outcome. So this is head, head, tail. So 2/3 times 2/3 times 1/3. For the next one, it's head, tail, head. 2/3, 1/3, 2/3. And last one is tails, heads, heads. So 1/3, 2/3, 2/3. I'll compute or add those together, and I get 4/9. Everybody's okay with that? Just like we did last chapter. And now, if we have just like 3 trials, it's not unrealistic to do this still. But what if instead of tossing this coin 3 times, what if we toss the coin 60 times? Do you want to draw a tree diagram with 60 sets of branchings? No, shoot me in the face. I have no part of that. Like, that sounds miserable. There's got to be a better way. What we're going to do right now is do this example again, make some observations about things we could have noticed from this example, and use that to generalize this to a situation where we can do this without having to draw any kind of diagrams. Okay with that plan? All right, so some observations that we could have made from that previous example. The end result is all that matters. I notice that the probability of getting exactly 2 heads didn't change with the order that the 2 heads occurred, right? So like they all had the same probability, whether I did heads, heads, tails, or heads, tails, heads, or tails, heads, heads. The probability for each one of those 3 outcomes was the same. That should always be the case in a binomial distribution. So all I'm going to worry about is the probability of figuring out for one of those outcomes, and then figure out how many different outcomes of that type I'm going to get. That's called a combination. And if I can figure out the probability of one of these outcomes, and I can figure out how many outcomes like that I'm going to get, to calculate the probability, I just multiply those 2 numbers together then. So that's my observation here. So if I want to build this out, let's do the same example, except this time we're going to do 6 tosses and kind of use these observations that we've just made to start generalizing this. So I'm not going to draw a 6-branched tree diagram because 3 branches basically filled up my PowerPoint. 6 is going to look ridiculous. No one's going to be able to read anything. I don't know. I actually think I could fit it in there. Not using something like 1 font or 1-point fonts or something. So the first thing I want to observe is satisfies all the conditions for a binomial distribution. The conditions are that there's a finite number of trials, in this case 6 because we're flipping the coin 6 times. It's success or failure, I either get heads or tails, 2 outcome. The probability for success is known, it's 2/3 and it's a coin, so it's going to stay fixed at 2/3. And I know that these coin flips are independent of one another, so that's the conditions for a binomial distribution. Everybody's cool? Okay. So again, knowing that this is binomial isn't going to help us right now, but the pattern that I pick up right now, I'm then going to apply to all binomial distributions. So that's kind of why we're doing this now. So again, I find that this situation, this random variable x, is binomial 6, 2/3. So if I can just, because I know that the probability for each outcome is identical, I can just pick one of those outcomes and calculate the probability. So here I'm going to choose to calculate the probability for heads, heads, tails, 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 tails. Okay? What's the probability of getting 1 head? Of getting heads? It's in the problem. 2/3. Okay, and then to get a second head, multiply by 2/3. And then get a tail, multiply by 1/3. And I'll do that 3 more times. So that's the probability for 1 outcome. Everybody feel okay there? Now I need to count how many combinations I can make where I get 6 coin flips and get 2 heads. So we have a formula to calculate this. to count the number of combinations. So there's a couple of different ways you can denote it. On your calculator, the notation looks like NCR. I don't know who does it this way. Must be somebody, probably the people in Europe or something. And then most commonly in a textbook, you'd see it combination related this way. Kind of looks like a fraction, but there's no horizontal fraction bar. Make sure if you're using this notation, you don't put a fraction bar, because all of a sudden you've changed it from a combination to a number, like just a fraction. But the formula is this. What do these exclamation points mean in a math formula? Does it mean N? No. That's the factorial symbol. So for example, in math class, if you have 3 factorial, that means 3 times 2 times 1. Right? That's all the exclamation point means. It's the factorial symbol. So if n is the total number of trials and r is the number of successes, in this problem, we're going to do 6, choose 2. So we want to figure out in 6 places how many different ways can we put 2 of them in there. Blah, 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 blah. Oh, also note by definition, 1 factorial is 1, and 0 factorial is 1. That seems odd, right? 0 factorial is 1. So what these factorials are used for is counting the different ways you can arrange something. So if you have one thing, how many different ways can you arrange it? One way. If you have no things, how many different ways can you arrange it? Still one way, right? It's just like there's the arrangement where there's nothing there. That's why 0 factorial is 1. It's not a math reason, it's like a definitional reason. All right. Here I note that the number of combinations where I get 2 heads is the same as the number of combinations where I can get 4 tails. So 6 choose 2 is going to be the same as 6 choose 4. Everybody's okay with that? Because if there's 6 things and they're either heads or tails, 2 heads is going to be the same as 4 tails, right? So the number of ways of doing 2 heads has to have 4 tails in it. So it's also going to be the number of ways you do 4 tails. All right. So we can take our probability and multiply it to our combination. So I have 6 choose 2 times 2/3 squared times 1/3 to the 4th. Plug that 6 choose 2 into my formula for combinations. Balloon out my factorials. Do a little reducey, simplify that stuff down, multiply it together, and there's my approximation. Does that feel okay with what we did there? All right. What I want to do now is to generalize this out from this specific problem to just be the probability of x equal to x for any binomial distribution. So if I do that, if x is binomial, the probability that x is equal to r is n choose r times p to the r times 1 minus p to the n minus r. So in our previous problem, n was 6 and r was 2/3. So we had 6 choose 2, 2/3 to the 2 times 0.4, that's 1 minus, 1/3, 1 minus 2/3 to the 6 minus 2 or 4th, right? So this is the same formula that we have. We've just now generalized it to n, p, and r. And here we just note that sometimes 1 minus p we write as q, where q is just the probability of failure. You don't need to memorize this formula. It'll always appear on any equation sheet on your quiz or test and even on the IB exam. All right. Rewrite the above situation using symbols. X is binomial distributed with 6 trials and a probability of success equal to 0.2. So n is 6, p is 0.2. So I just write that. this statement here and this symbols here mean the same thing. Okay, sometimes you'll be given it symbolically, sometimes you'll be given it in words. Should be able to read it and like move back and forth between the two. Everybody's okay? Okay. We're going to take this situation and find the probability of getting exactly 4 successes. So what is that symbolically? That's the probability of x equal to 4. So if I plug into our formula, n is 6, r is 4, p is 0.2. So I have this. Everybody's good how I plugged in? I go to my formula for combination. I balloon out those factorials, reduce some stuff down, simplify, and there's my answer. So far, so good? Okay. The probability of getting at least 1 success. What does at least mean in mathematics? Greater than or equal to, right? Remember back in chapter 8 when we ran into these at least or at mosts? Oftentimes we use that complement rule, like 1 minus the complement, to make our lives easier. Oftentimes I'm going to be using that same trick here. So at least 1 is greater than or equal to 1. So if I wanted to do this directly, I'd have to find p of x equals 1 plus p of x equals 2 plus p of x equals 3 plus p of x equals 4 plus p of x equals 5 plus p of x equals 6. Yuckarooskies. Or I can do 1 minus p is not at least 1 success. The negation of it less than or equal to, the negation of greater than or equal to is strict less than. So less than 1 success is only 0 successes. So I'm going to turn this into p minus, p of x is less than or equal to 1, or greater than or equal to 1, equals 1 minus p of x equal to 0. And I can compute that real quick using my formula. Again, remembering that 0 factorial is 1. So this is the statement that we've made. So there's my answer. Everybody's okay there? So if I want the probability of, getting 3 or fewer successes, that's the probability of x is less than or equal to 3. So if I did that directly, it would be probability x equals 0, probability x equals 1, probability x equals 2, probability x equals 3. If I did it by, This thing is being real laggy. Okay, sorry. So this is the slide. Probably getting 3 or fewer successes. So again, that's less than or equal to 3. So again, I could do it directly, calculate 4 probabilities. I could do it with a complement, but I'm still calculating 3 probabilities. There's not much difference apparently in the slide. I decided to go with the direct version, probably just for variety's sake, even though 3 is less than 4. So we did that. I banged those all through those formulas, and then this is my answer. So far, so good? Okay, let's look at another situation. Find the probability that I get a bus to work on any morning is 0.4. was the probability that in a working week of 5 days, I will get a bus exactly twice. So if I want to rewrite the situation in symbols, first I should define whether this is a binomial distribution or not. So, are there a finite number of trials? Yes, how many? 5. 1 day for each of the week. Do I know the probability of success? What is it? Good. Do I know, are there 2 true outcomes, success and failure? What's success? That you take the bus to work. What's failure? That you don't. Very good. Is the probability fixed? Yes. Are the trials independent? Yes. So it's a binomial distribution. So we can say then x is related to the binomial distribution 5, 0.4, and we're looking for the probability that x is equal to 2. Everybody feels happy with that? So if I want to solve the problem, I'm going to take x equal to 2 and plug it into my binomial formula and grind away. Boom, done. Just plug it into the formula. Guess what, though, guys? You don't have to do this by hand. This is all built into your calculator. If you have your graphing calculator with you, I recommend you taking it out to follow along. If you want to borrow one of mine to follow along with, there's 4 sitting on my desk, and you're welcome to grab one if you so choose. Or just look on with your neighbor, that's fine too. So all of your probability distributions, they all live in the distributions menu, so you'll press second and the vars button. That's what's circled in yellow on my picture. You'll scroll down until you see binomial PDF. It's option A on my calculator. PDF stands for probability density function. Notice below it is also binomial CDF. That's cumulative or probability cumulative function. Here's how you know which one to use and when. Are you ready to hear? PDF is if it's x equals. CDF is going to be for an inequality. Okay? So if we're doing a probability x equals x, PDF, if we have a probability x inequality x, it's going to be a CDF. But you might have to do some messing around before you can actually type in your calculator. Because the CDF on your calculator only works for less than or equal to's. Okay? All right. So I'll pick binomial PDF. I'll fill out the table. 5 trials. Probability of success is 0.4. Number of successes is 2. And I'll press enter and blammo. Spits it out for me. Plugs everything into the formulas for me. Ooh, I like that, Mr. Kulik. Pretty nice, right? Yeah. Okay. Now notice I've changed the problem. What did I change in the problem presentation here? At most twice. What does at most mean? Less than or equal to. Right? So if it's at most twice, it should be probably x is less than or equal to 2. So that means I could calculate these three, where I could do a PDF for this one, and then plus the PDF for this one, plus the PDF for this one. Or I can do it as just one CDF. That's what I would do, because 1 is less than 3. So I will just do binomial CDF. N is 5, P is 0.4, R is 2, and blammo, spits it right out for me. Make sure you do the CDF. How'd that work? You guys following along? Okay. Let's do another example. When administering a drug, it is known that 80% of people using it were cured. The testing program administered the drug to 2 groups of 10 patients. What's the probability that all 10 patients were cured from both groups? Okay. So what's different about this problem than the previous one? You have 2 separate binomial experiments, right? You have group 1 and group 2. Everybody see that? When we read the question, you picture it in your head. Are both groups binomial? Is there a fixed number of trials? Yes. How many trials are there? 10. Do we know the probability of success? What is the probability of success? 0.8. Are there just 2 true outcomes? Yes. Success is they get better. Failure is they don't. Right? Is each individual trial independent? Does a person getting better depend on the person before them? No. So they are independent. So both trials are binomial. So I will calculate the probability for trial 1 with 10 cures times the probability of trial 2 with 10 cures. Everybody's okay with that? So that's easy to do. Probability, since it's binomial, of 10 cures is just going to be binomial PDF, 10.810. There's my number. So if it's both groups, it's going to be P of x equals 10 times P of x equals 10, or P of x equals 10 squared, and there we go. Everybody feel okay? There's another way of thinking about this, though. How else could we have conceived of this? What do we know about the trials of a binomial experiment? They're independent. And both of these are essentially the same binomial experiment, right? So instead of thinking of this as 2 separate binomial experiments, what if I thought about it as one binomial experiment with 20 trials where I was looking for 20 successes? I could do that and it's still going to give me the same answer. So you could have done that also. This is the more natural way of thinking about it, but the other way is still correct because of independence. Everybody's okay there? Here's the catch, though. It wouldn't have worked if it was 9 successes and 9 successes. You couldn't have done like 18 successes out of 20, because that could have been 10 in a row and then 8 in a row, which wouldn't have fit the criteria. It's only because it was in either all or none. All right. Next up, we want to talk about mean or expectation for these binomial distributions. So again, mean, expected value, expected count, expectation all mean the same thing. For a binomial experiment, it's real easy. All I have to do is do n times p. That's it. That'll give me the expectation. That'll give me the mean. That'll give me the expected value. They're all the same thing. So if I have a fair coin, I'm going to toss it 4 times. Coin flips are binomial experiments. We've already talked about that previously. There's 4 trials. The probability, since it's fair, of success is 0.5. 4 times 0.5 is 2. So I expect if I flip the coin 4 times, I'd get heads twice. If we change it to 5 times, I'd expect to get 2.5 times getting heads. Is it fine that that doesn't really make any sense in the context of the problem? Yes, expected values don't need to be like realistic in terms of unit, right? 2.5 times of getting heads is fine for expectation. So a biased die is thrown 30 times, and the number of successes seen, a number of 6s seen is 8. The die is then thrown a further 12 times. Find the expected number of 6s for these 12 throws. First things first, is this a binomial experiment? Do we have a fixed number of trials, a finite number of trials? Yes. What is the number of trials? Not 30. It's 12. Right? Do we know, is there 2 true outcomes, success or failure? Yes. What is success? Getting a 6. What's failure? Not a 6. Everybody's okay? Now, not a 6 could be, 1, 2, 3, 4, 5, but we don't care. What is the probability of success? What's the probability of success? Come on, you stupid machine. Just sitting here. Keep thinking. I'm just going to mess around with this stuff here. I think I really broke it now. What is it, though? We've had a minute to think while I was jiggling the pieces here. It's 8 out of 30. That's correct. What type of probability is that, though? Remember, there's 2 types of probability, theoretical and experimental. So experimental. Why is it experimental rather than theoretical? Yeah, it's based on results of like an experiment, right? Okay, so we did that. Binomial. So expectation is n times p, 12 times 8 out of 30, or 4 out of 15 if you wanted to reduce, 3.2. What's that mean in the context of this problem? If I roll the die 12 more times, on average, I'd expect to see 3.26.
That's all of it.
Okay, thank you.
Okay. Sorry to interrupt the class.
They'll forgive you.
Will you?
Isn't this so much fun? All right. the next thing we're going to talk about is how to compute variance. So remember, variance is a measure of spread. Good news is it's an easy calculation for binomial. Just n times p times q. Remember, q is the probability of failure. And if I want standard deviation, remember standard deviation is just the square root of the variance. So it's just going to, the standard deviation is just square root n times p times q. Mr. Kulik, I like this. It's so simple. All right, so in a large company, 40% of the workers travel to work on public transportation. A random sample of 15 workers is selected. Find the expected number of workers in this sample that traveled to work on public transport. Now, you might be tempted to dive right in and do, n times p. Don't. You need to do something first. You need to verify that this is a binomial experiment, because in one more section, we're going to get a second type of probability distribution. So you have to be able to read the question and pick out which type of distribution it has, because the expectation and variance formulas and stuff are going to be different. Okay. Is this binomial? Is there a fixed number of trials? Gosh darn it. Yes. What is the number of trials? 15. Is there 2 true outcomes? Yes. What is success? Great. And what is failure? Perfect. Is the probability of success known? Yes. What is it? 0.4. Is it independent? Yes. The probability of what one worker does not depend on the worker before it, right? Okay. So, since it's binomial, we can just do n times p. So 6. So we'd expect that 6 workers in this group travel to work on public transportation. Everybody's okay? If I want the standard deviation, first I calculate the variance. Since it's already binomial, we already did that, I'll dive straight in. N times p times q. Remember, q is 1 minus p. So 15 times 0.4 times 0.6, 3.6. Then to get the standard deviation, I just take the square root. I get about 1.9. Everybody, it's okay? So that means that a randomly selected group of 15 workers would on average have 6 workers travel by public transportation, and any such group on average would be 1.9 workers away from the expected value. So if I took another random sample, I'd expect to get 6 workers taking public transportation plus or minus 1.9. Right? So as many as 7.9, maybe as few as 4.1. So far, so good? That's it. Let's do some of the, oh dear, look at this mess. What is my window? It is very angry at me right now for whatever reason. Like, no, you can't just pick this up and move it. Stretch it and fill the screen again. All right, so let's run through some of these examples. I recommend that you have your calculator out with you, because how are we going to be calculating these probabilities? I'm going to use our calculator to do it, use those distributions. All right. There are 12 students in a class, and there are exactly 5 girls and 7 boys. You want to determine the probability of selecting 3 boys in a row with replacement if you're to select only 3 students at random. Let X be the event that you selected a boy. Show that X satisfies the conditions to be a binomial distribution. What are the 4 conditions I need to check? Okay, well, let's start at that's true, but we like to start at the beginning. Finite number of trials. Is that true? Yes, how many trials are there? 3. Great. Are there 2 true outcomes? Yes. What is success? Boy. What's failure? Not a boy. It's tempting to say girl, but let's just say not a boy, because it's, like you don't want to imply, not because of the gender thing, but in general, like 6 and not a 6, right? Do we know the probability of success? And what is it? Seven out of 12. How'd you get that, Olivia? 7 boys out of 12. Is that probability fixed? Yes. Why? Because it has replacement. Yes. And that's also what guarantees independence, right? Everybody's okay with that? All right, so we know that. That's part A, right? We just showed that the conditions satisfies the conditions. We just said them aloud. There's no math to show. You just, you write the statements down in words. Write the binomial distribution for the situation above in the form X relates to binomial NP. What's N? I think it's still 3, my man. Make sure I'm not going crazy. Yeah. Right? It says 3 students selected at random. What's P? 7 out of 12, right? We good? Part C says find the exact value of picking exactly 2 boys in the 3 trials. What am I going to use to compute this? What function on the calculator? PDF or CDF? PDF. When you bang that through the calculator, you should get about 0.425. So far, so good? Okay. Let's do the next one then. Find the probability X is less than 2 using your GDC, your graphic display calculator. Can I find the probability that X is less than 2 with my calculator as it's currently written? No. What is the only inequality that my calculator can handle? Right, but what inequality can CDF handle? Only one. has to be less than or equal to. Now, that's not a problem for us, because what does less than 2 boys really mean? 1 or 0. So wouldn't that be the same thing as x is less than or equal to 1? Yes. Now I can CDF it. Yes. Sure. All right. Do I need to do anything to my calculator in order to do this one? No, it's good to go right the way it is, right? Just CDF it. Those of you that are following along, are you guys getting the decimals that I'm writing down here? Make sure if you're following along, you're checking to make sure you're getting this into your calculator correctly. It's half the battle, right? Let the calculator do all the heavy lifting for us. We're all about setting it up, and the calculator's about knocking it down, right? All right. The next one. Who can do part A for us and tell us the answer? You're going to have to go fast to beat Geraldine. She's already on it.
No, I don't think I can do it right. The number makes sense. Oh my God, these are awful.
Anybody got it yet? I think it's 3. Okay, who can do the next one? Part B. Again. What do we get? Did you get it, Geraldine? Yes! Oh, yeah, it's my messy 7s. What do we have to do to see? We have to do it as a complement. That's the only way you're going to turn the inequality symbol from greater to less than. What's the negation of greater than? Less than or equal to. And now we're in business. Is everybody okay with what I did there? Use the complement rule in order to flip the inequality from greater to less than. when we do a complement of an inequality symbol, it always changes from, like strict to or equal to, or equal to strict. So that's always going to be the way it works. So if you think about it, b greater than 6 would include 7 and 8 successes. So the complement should include 6, 7, or 6, 5, 4, 3, 2, 1, 0 successes. So less than or equal to 6. Right? If you're confused of whether it should be or equal to or not, write out what should be included in one and the other, and it should usually be pretty obvious. Okay. Let H be the event Mr. Chun checks in homework. The probability that Mr. Chun will check in homework on a given day is 0.85. Assuming that each day is independent, write the following events in correct notation and then use your GDC to solve for the indicated probability. Mr. Chun checks in homework 4 days in a row. What do we think here? What is the N? What is the R? If it's 4 days in a row, it just, you have 4 days, you need 4 successes, right? Doesn't say in a given week, we do 4 days in a row. That's a different question. Just 4 days in a row. So I can just do that as a binomial PDF 4.854. When I do that, I get 0.522. Is everybody okay with that? The next one says, for 3 consecutive days, Mr. Chun checks in homework exactly once. What is our N? Three. What is our R? 1. In a 5-day week, Mr. Chun checks in homework exactly 3 times. What is our N? 5. What is our R? 3. It's our random variable. In a 5-day week, Mr. Chun checks in homework at least 4 days. What am I going to have to do before I can go to my calculator? Yeah, I got to turn that frown upside down. When I take the complement of greater than or equal to 4, what do I get? Strict less than 4. Can I do that on my calculator, though? No. What does the inequality have to be? Less than or equal to. What does less than 4 days mean for us, though? 3 days, 2 days, 1 day, or 0 day, right? So that could be the same thing as less than or equal to 3, right? Now I'm ready to CDF that bad mama jam into my calculator. When I do, I get that. In 2 consecutive 5-day weeks, Mr. Chun checks in homework at least 4 days each week. What's the key here? Is it the same thing as happening 2 times in a row, right? 2 consecutive weeks. So I'll just take my previous answer and square it. What do you guys think? Nah? So the observation here should be that the actual computation, very easy. The calculator handles all of it. What's the hard part? Getting the setup so you're getting the right stuff into your calculator. Okay, this is going to be a chapter where really doing the homework problems, like reading them and thinking about them and understanding how to decode the language into symbols to get it into your calculator, is going to be the key skill. The actual like computing things, the calculator will handle it all for you. You just have to be able to get it in there the correct way and interpret the question in the correct way. So reps are going to make a big difference in like reading the problem and thinking about them and like going ahead back and forth and grinding a little bit on the homeworks, like are going to be really important. Don't just copy the answers out of the back of the book on this one. Like you do need to try them. It will make a big difference. All right. The next one says find the expected number, i.e. the mean, the variance, and the standard deviation for each of the following binomial distributions. I'll do the first one. Since it's binomial, there's my expectation. N times P. Since it's binomial, there's its variance, N times P times Q. And I know that the standard deviation is always just the square root of the variance. All right. Who can tell me the expectation for part B, or at least just tell me what to write to calculate it? What's N? N times P. Done, right? I'm not going to compute it. I'm just going to set it up. The variance is N times P times Q. Well, we know what N and P is from the previous one. How do I find Q? It's always 1 minus P. All right, now for realsies. Oh my God, like stop. Somebody really tell me, how do I find the expectation for Z? Don't make me call on you. Thank you. Perfect. How do I find the variance? One minus 0.27 is fine. Yep. And how do we get the standard deviation? Yeah, your variance. Everybody's cool? Again, super easy, right? What's the catch? You also got to know that it's binomial, right? How did I know each of these were binomial? Literally tells me. Okay? But that's how I know it's binomial, is like it's told me in the problem. All right, last example, I do believe. It says you determine that your chances of winning a game of rock, paper, scissors is 35%. You decide to play 6 games of rock, paper, scissors with your friends. Suppose R is the number of games you win. Find P of R equal to 2. Get your calculator moving. What is it? Which binomial is it? PDF, CDF? Good. How many trials? What's the probability of success? How many times are we successful? What's going to tumble out of our calculator like magic? That guy. If we want the probability distribution for R, what does that mean? It means that I need to give the probability for each possible outcome or each possible event. So I need to do P of R equals 0, P of R equals 1, P of R equals 2, R equals 3, etc., all the way up to P of R equals 6. Guess what? Yeah, but this looks like a lot of things in my calculator. Guess what? We can do it in one shot. So what I'm going to do is I'm going to go to the y equals. And into y1, I'm going to do a binomial distribution. So second, vars, binomial PDF. The number of trials is 6. The probability of success is 0.35. The value of x is going to be x. And I'll hit paste. So it's just in Y1. And then I'll just look at the table. So for values 0 to 6, there's the associated probabilities. Bingo, bango, bongo. We're done. I just copy them onto my sheet of paper. I got 6 probabilities for the price of 1. That ain't too shabby, Mr. Kulik. Right? Better than doing it 7 times. You get what I did there?
Yes.
Quite helpful, right? It's a nice trick. All right, I'm not going to copy them down because, like, ugh. Part C says, find and interpret the mean for R. How do I calculate the mean for R? The mean is the same as the expectation. So just n times R. That's the value. How do I interpret that? I know. When I play 6 games of rock, paper, scissors, right? Everybody cool? Okay. Find and interpret the standard deviation for R. So I need the variance first. N times P times Q. So the standard deviation is the square root of that. But what does the interpretation then mean? What does that mean in the context of this question? That on average, I'd expect to win 2.1 plus or minus 1.7 games of rock, paper, scissors against my friend. Everybody feel okay? All right, so that's going to close up section 2 for us. We'll stop